Hey, we have here another integral from the MIT Integration Bee 2010. We're on to problem number 20. We have the integral from 0 to pi over 2 dx over sine x plus secant x. The first thing I see is that we don't really like having sine and secant. Those don't really work well together. We'd rather have like sine and cosine or secant and tangent. So this is potentially a problem, but the one thing I like is I like these bounds because I feel like we might be able to use this. The bound seems like it might be setting up a good substitution where we could use the complementary angle formula. But what I want to do first is address this sine and secant thing. What I'm going to do is I'm just going to multiply top and bottom by cosine, thinking that I can clean up the secant right here. So doing the rewrite, now we're going to have cosine x in the numerator, and then we'll have sine x cos x. Now, cos x times secant x is just going to be 1. And so you can see the purpose of that. Now we have everything in terms of sines and cosines. We don't have any secants or anything else going on. And next I am going to use these bounds and try to do a substitution. So the substitution I like to make with the bounds like that is going to be just pi over 2 minus x. Then we can rearrange and we get a value for x, which is just going to be pi over 2 minus u. And I'll get my derivative here. So dx is going to be just minus du. I'll make the substitution. We plug a pi over 2 in here. Our upper bound's going to be 0. And our lower bound's going to be pi over 2. This kind of substitution just flips the bounds. Then for cosine, so we have our x value pi over 2 minus u, so I'm just going to plug that in here. Our dx is going to be minus du. Then in the denominator, we're going to have sine pi over 2 minus u times cos pi over 2 minus u, and then we'll have a plus 1. Okay, and from here, like I mentioned earlier, we can use complementary angle formula, which is going to work nice. So we'll notice for cosine pi over 2 minus u, we have sine of u, and for sine of pi minus 2 minus u, cosine of u. So that's going to allow us to transform everything we have here. Before I do that, I'm going to take this sign, this minus sign, bring it outside the integral, and just use it to flip the bounds. Okay, and that's nice because you'll notice we have the bounds now the same as we had in the original integral. And so I'm going to rewrite this using the complementary angle formula. But one other thing I'm going to do a variable change. Because this is a definite integral, I can change the variable to whatever I want. So I'm going to change back to x. Okay, and now you notice that our cosine terms have turned to sine, our sine terms have turned to cosine, but the interesting thing is it doesn't change this because it just reversed the order. So we went from sine times cosine to cosine times sine, but the order doesn't matter, and we end up with that. So next what I'd like to do is go back, we'll call this original integral we had I, but all we've done is transform it. So all these things are I, so this one's I. I don't care about this one, but this one I'm also going to call I. And then so what I can do is I'm going to add this one to this one, so that we have two copies of the integral. So we're going to have 2i. Because we have the same bounds, the same variable, and the same denominator, these are going to be really easy to add together. So let's rewrite these added together. Okay, so now we've kind of smashed these two together. We've added the sine x and the cosine x in the numerator, and we have the same denominator here. But the thing I notice here is this integral isn't that easier. This is not automatic. In the past, when we've done like symmetry problems or King's principle, a lot of times the integral we get after adding together is really simple, or it's just 1. In this case, it's not quite so easy, so we're going to have to do some more work. But let me clean up the board first, and we'll continue. Okay, so at this point, it does look kind of tricky because we don't really have a great way. I want to do a u substitution, but it doesn't really look like it's working the way we have it set up here. We're going to say I want this numerator to be my du. So we're kind of like wishful thinking. We're going to before we set our u, we're going to set our du in advance. And then basically, if we just integrate this, we get our u. What our u has to be is going to be, this is going to be sine x minus cos x. But the problem is we don't have our u anywhere, right? We don't have our u in the denominator where we want it. What we're going to do is kind of try to create that. What we're going to do is try to relate this to this. So I'm going to take my u and square it. So we're going to get, and this is a little bit of a leap of faith. I mean, I know it works, but if we square this, we get sine squared x plus cos squared x, and then we're going to have minus 2 sine x cos x. But notice sine x cos x, this is the thing that we want to find. So really all we need to do is rearrange this and solve for this, and then we have something to plug in here, and then we have a way to get our u value back into our denominator where hopefully we can use it. So of course this piece right here is just equal to 1. So we have 1 minus 2 sine x cos x. Then what I'm going to do is we'll add this and bring this on the other side. So we're going to have 2 sine x cos x, and subtract this piece off is going to be equal to 1 minus. Then here we're going to have our sine x minus cos x squared. And we just need to divide by 2 on both sides, right? And so now we've isolated this, and we have an expression for it. So now I'm just going to take this expression and plug it back in, and we'll continue. Okay, so now I've taken that expression that we found on the last board and plugged it in here for our sine x cos x. And now we just need to do a little more simplification. What I can do with this 1 is we can get a common denominator, and I can write this as 2 over 2. And then so when we add these together, this 2 plus this 1 over here, this is going to give us a 3 over here. Okay, and then I'm just going to take this 2 that we have in the denominator and bring it out front into the numerator. And then before I do my substitution, I'm just going to cancel the 2's here on both sides so that now we're just solving for our goal, just the integral that we want. But now we can make our u substitution. So what I'm going to do is we're going to plug pi over 2 in here. So first let's update our bounds. So pi over 2, sine of pi over 2 is 1, cosine pi over 2 is 0. So we're just going to have 1 for the upper bound. Then plugging a 0 in, sine of 0 is 0, minus cos of 0 is 1. So we're going to have minus 1 here. Then like we set it up, our denominator is just going to be du, what we have right there. We've got our 3 minus, and this is our u right here, so we're going to have 3 minus u squared. Just because I want a perfect square here, I'm going to kind of create it. So instead of 3, we're going to write this as square root of 3 squared. And one other really minor thing I'm going to do is, because this is an even function, because this term squared, what I can do is in the bounds go from 1 to minus 1. They're symmetric, so I can change this to a 0 and bring a 2 out front. Okay, from here on this integral, we could finish this off with partial fractions, but because this is in a standard form, I'm going to use this formula. Just noticing this formula is in the exact right form. We have square root of 3 is going to be our a value, and we have our variable over here. So let's just do this. We're going to have our 2 out front. 1 over 2a is square root of 3, so we're going to have 1 over 2 square root of 3. Then we have natural log, absolute value. We have our a, so we're going to have square root of 3 plus u over square root of 3 minus u, and I was going to do plus c, but we actually have to evaluate it from 0 to 1. Now I'm going to cancel these 2's, right? So we just have 1 over square root of 3 in front. So then next let's evaluate at 1. So we're going to have 1 over square root of 3, natural log, then we're going to have square root of 3 plus 1 over square root of 3 minus 1. And both these are positive, so I'm just going to drop my absolute value. Then next we'll have evaluating at 0. This is actually going to, when we plug 0 in for u, we're just going to have square root of 3 over square root of 3, which is 1. Natural log of 1 is just 0. So I'm just going to remove this piece. And then this is fine as an answer, but I think just to clean it up a little bit, I'm going to rationalize this by multiplying by the conjugate right here. So when I multiply this out, we're going to have 3 minus 1, or 2 in the denominator. Then in the numerator, we're going to have a 3 plus a 1 is a 4. Then we're going to have plus, just distributing out 2 square root of 3. But I can just divide the 2 through here and cancel here and get a 2 here. So for my final solution, we're just going to have 1 over square root of 3, natural log 2 plus square root of 3. So that's it. Thanks everyone for watching. Have a great day.